All right, so tonight I am going to talk to you folks about covalent bonds, which is a little bit cheating um, because you've already learned about covalent bonds since you had to do that little activity, making an infographic for me. That's what you get. But we're going to go into a little bit more detail, and in particular, I want to talk to you folks about how we use the octet rule to help us explain what covalent bonds and the atoms associated with covalent bonds actually look like. Now, we now know, as a result of your nice little infographic, that covalent bonds are all about sharing of electrons. And it's always, in the case of what we're doing, it's sharing of a pair of electrons. And, that's supposed to be a minus, not an apostrophe. Jeez. And this is very different, obviously, from ionic bonding, where you have a transfer of electrons. Now, what's cool about covalent bonds and molecules in general is that they can form bonds either with one other atom, so you can have two atoms that make up a molecule, but you could also have molecules that are millions of atoms long, like DNA, for example, would be something that maybe it's not quite a million, but a heck of a lot. And the other thing that we need to understand too is that there's something called a molecular formula, which is equivalent to the formula that we saw with compounds, in that it tells us the number of atoms and the type of atoms that you would have in a single molecule. So for example, let's say we take something like glucose. Glucose has a molecular formula of C6H12O6. Now, in the case of ionic bonds, this was a great thing to have because we certainly knew that when you had NaCl, you knew that the empirical formula meant there was always a 1-to-1 ratio between the number of Nas and the number of Cls. And if you had MgCl2, you also understood that you'd have to have 2 Cls for every 1 Mg in order to have a neutral compound. But the problem here with molecules is that we can have something that has the exact same molecular formula. For example, fructose. Ooh, that's not how you spell fructose. And in fact, you should know that I deliberately selected these two compounds because they are going to be very important things for you to understand next year when you take biology. Remember. But anyway, the bottom line here is that fructose has the exact same molecular formula. So how does one go about distinguishing between those two things? Well, that's where we have something called structural formula. And a structural formula is something that we would always want to make sure that we showed with regard to a molecule. Okay? So know that these structural formulae, they are going to be things that you still will use Lewis dot structures, just like we did with ionic compounds. And we also are going to be following the octet rule. Remember the octet rule, where you want to satisfy an atom by having 8 electrons in its outermost orbital, or set of orbitals. So let's take a look at something like that. Do I have room here? You know what, I'm going to move to the next page. I want you to imagine that I'm working with the element fluorine. And you know that fluorine, if you look at it, it's a halogen, so that means it has 7 valence electrons. So I'm going to go ahead and add those on there. Here's 1, 2, 3, 4, 5, 6, 7. Okay? And let's say that I'm going to have another fluorine, and I want to combine these two fluorines. And in fact, you should remember that fluorine is one of those things called the Honkelbriefs. It's one of the Honkelbriefs. And by that I mean they are diatomic when they're found in nature, meaning they are paired up with one another. You would never find fluorine, an atom of fluorine by itself. It would always have a buddy next to it. Well, I hope you can understand here, just by looking at this, that if I were to combine these two fluorines to make the diatomic molecule, fluorine, that if I pulled them together, they would actually share an electron pair. So it would look like this. Those two right there that are by themselves, right, this guy right here and this dude right here, they're initially by themselves. They now will come together and they'll be shared evenly between the two fluorines. And I'd still have my other valence shell electrons cruising around there. But I want you to notice here now that this satisfies the octet rule for both atoms here. So I have 1, 2, 3, 4, 5, 6, 7, 8, which is exactly what I want to have for this guy on the left side, so he's happy. And then similarly, I have 1, 2, 3, 4, 5, 6, 7, 8. That's what I'm talking about, the sharing that's going on there. So that guy is also satisfied. So they're in a constant handshake here. Whenever the fluorine on the left says, hey, I need my 8, he can go over there and grab up 8. Whenever the fluorine on the right says, hey, I want my 8, he can grab up his 8. So together, they can be very happy and in a nice, comfortable state, a low energy state. All right, so now let's take a look at another molecule. In this case, we're going to look at ammonia. Now, ammonia is not the same as ammonium. Ammonium is the polyatomic ion, NH4+. Ammonia is a neutral molecule. There's no charge associated with it. And its molecular formula is NH3, no charge. Okay. However, when we look at the Lewis dot structures for these, let's take a look at nitrogen. Nitrogen, if you remember where it is, it's going to have 5 valence electrons. Okay, so we have 1, 2, 3, 4, and I'll just put the extra one up here on the top. And then we have hydrogen. And hydrogen, I'm just going to have these guys in blue. And we have to have 3 of those, as indicated by the formula, right up here, NH3 formula. And I think you can see how this is going to fit together pretty nicely in order to satisfy the octet rule. So I'm going to go ahead and bring my nitrogen down here, and with its Lewis dot structure, just like that. And then each one of these hydrogens I can pull in. Okay? So you can see here that the nitrogen is entirely happy here. It's got 1, 2, 3, 4, 5, 6, 7, 8. And hydrogen, is hydrogen happy? Why is it that hydrogen can have 2 electrons and still satisfy the octet rule? You should know that. I'm not going to answer that because that seems like a great test question. But hydrogen is entirely happy in this situation, in that it has its 2 here, in this case it has 2 here, in this case it has 2 as well. The one thing that you will note here that's different is that we do have this situation. Right? There's nothing associated, there's no atom attached to that pair of electrons. And we have a name for that. We call that, no surprise here, it's a good name, oh, am I going to have room? Oh, phew. An unshared pair of electrons. Okay, unshared pair of electrons. So sometimes that will happen where you're going to have an unshared pair of electrons, and that's totally fine. It still satisfies the octet rule. All right. The other thing we have, let me go to a new page here, is that there are cases with molecules where we have multiple bonds. Let me just go back here. Each time we have a pair of electrons here, so again right here and right here, that is the bond, and it's a single bond that exists between each of these hydrogens and that central nitrogen. Over here, same sort of thing. We have a single bond that exists between those 2 fluorines. Right? All right. So what if we do something instead that has multiple bonds? Did I go to that second page? What happened? No, maybe not. All right. So here we go. Let's take, for example, the molecule formaldehyde. Now, I always like to bring in examples from biology, and formaldehyde used to be a preservative that we used, um, and we would keep like fetal pigs or squids or whatever in formaldehyde to keep them from rotting. We don't do that anymore because it turns out that formaldehyde is actually a carcinogen, which means it causes cancer. So we have formaldehyde, and know that the molecular formula for formaldehyde is H2CO. Okay, and that tells us certainly that there are two hydrogens, a carbon, and an oxygen, but it doesn't tell us how they're arranged with one another. I mean, is the oxygen with the hydrogen? Maybe the oxygen is attached to the carbon. What's going on there? Well, that's exactly why we have the structural formula, so that it'll help us to understand what's happening. And let's go ahead and continue to do what we did before. What did I had blue for hydrogen. Okay, so I have two hydrogens here. We have carbon. I'm going to do carbon in black. And carbon has 4 valence electrons. And then I'll do red, I'll do for oxygen. And don't forget, oxygen has 6 valence electrons. 1, 2, 3, 4, and then 5, 6 paired up over there. Now, you could probably figure this out if you take some time to do it. Carbon is going to be our central atom. Okay? And then I'm going to bring in a hydrogen. I'm going to cozy it right up next to this carbon over here, and I'm going to put another of the hydrogens right there. And then that leaves us with the oxygen. Now you may look at this and say, wait a second, how are we going to possibly do this? Don't forget that I'm doing multiple bonds here, and that's going to really be a handy thing. Let me just, I'm going to erase this electron up there, and I'm going to put it actually right down there next to the carbon, and you'll see in a minute why that's important. Because I'm going to take this oxygen, and I'm going to do the same thing. I'm going to leave these two, these 4, I'm sorry, hanging out there, but I'm going to swing those 2 that are singlets, this one right here and this one right here. I'm going to swing those down right next to the oxygen over there. And then I'm going to grab up this oxygen, and I'm going to cozy it right up next to that carbon. Now, if I said moments ago, as you recall, that when you have 2 electrons, a pair of electrons, it represents a bond, and in fact it's a single bond. Now I have 4 of these electrons, always has to be an even, and now as a result I have something called a double bond. Now, looking at this situation, do these things satisfy the octet rule? Well, let's check and see. The hydrogen we've already established, all it needs is 2, so the hydrogens are totally fine. Yippee! How about the carbons? Well, we have the 1 here, 2, 3, 4, and then we have all 4 of these guys that are associated with a carbon. So in fact, carbon is fine. It has all 8 that it needs to satisfy the octet rule. And if we look at oxygen, we have the same thing. 2, 4, 6 of its own native electrons, plus it's got the 2 here from carbon that it can borrow, and so oxygen too has satisfied its octet rule. All right, the other one we have is a triple bond. Do I have enough room here? Let me clear this out here. And so an example of a triple bond is for something like ethyne, the molecule ethyne. And ethyne has a molecular formula of C2H2. And if I were to do this, don't forget carbon likes to have or will have 4 valence electrons, and then my hydrogens will have the 1. Oh, I think I was supposed to do hydrogen in blue. Oops. But I think you can see what's going to happen here. I'll have no problem attaching a hydrogen to the carbon over here, right? And same thing over on this side, right? And then that still leaves these, this, and this. Those 6 electrons need to be paired up. So how do we do that? We do that exactly the way you would think you would do it. They're all paired up here between the pair of carbons there. So then this is a triple bond as opposed to the double bond that you see going on right here. Now, to make things a little bit easier on us, rather than having these bonds be a whole bunch of dots, we can actually go back and make things a little bit easier. So let's go back to our ammonia here. Instead of having 2 dots, we can actually substitute two dots for a single line. And if that's the case, then I can rewrite my ammonia to look like this. I still will have my unshared pair of electrons up there, but now I'm going to have a line representing a pair of electrons. And then if I were to scooch over to, so this is my formaldehyde, I could do the exact same thing. I can have my hydrogen, and that will be bonded to a carbon, and bonded again, because there are my 2 and 2 right there. And in this case, I'm going to have a double bond to my oxygen. Now, I chose red as my bond. It's usually better to keep it one color, black or something like that. But I hope you can see that that's the exact same thing. And then I still need to make sure that I add my pair of electrons floating around on that oxygen. You got to leave those unshared pairs. In the case of oxygen, it's got 2 unshared pairs of electrons. And then lastly, if I wanted to show this with my ethyne, I could have hydrogen. I'm now going to go back to using black bonds because it's naughty for me not to be doing that. And you can see that that is what it would look like to represent a triple bond with lines instead of dots. All right, I think that's it. Yeah, good. This already went for 16 minutes and 40 seconds, so I'm going to go ahead and stop right there. I'm going to go back to our original front page here, covalent bonds and the octet rule, and good night.